Chapter 4: Atoms and Elements. Let's start this chapter by talking about the name of some of the important scientists in this field. Okay, let's start with Dalton's atomic theory. Based on Dalton's atomic theory, elements are made of tiny particles that are called atoms. Okay, atoms of the same element are identical. For example, all the atoms in hydrogen atom, or all the elements or all the atoms in hydrogen, they're all the same. In oxygen are the same. In lithium, they are the same. But different atoms consist of different element consist of different atoms, which means if you want to compare hydrogen and oxygen, they contain different atoms, which we will talk about it in more depth as we move on through this chapter. He also talked about when we combine atoms, we will form compounds. Okay, one of the examples, like for example, when you combine sodium and chlorine, we will produce sodium chloride. Okay, then sodium on its own is an atom, chlorine on its own is an atom, but when they are combined or joined together, they make a molecule. Okay, and molecules are joined together through chemical bonding. That's how molecules are formed. Different atoms, they join together through chemical bonding, or it could be same atoms, it doesn't matter. Also, following the law of conservation of mass, atoms are neither created nor destroyed. The only thing that changes is the arrangement of the atom. That's why we balance chemical equation. Okay, the number of the atom stays the same. Like this example, like hydrogen gas reacts with oxygen gas and produces water molecules. Okay, then as you could see on the left hand side, we have 2 hydrogen and 2 oxygen, which we call it a reactant side. And on the right side of the arrow, which we call it's the product side, we have 2 hydrogen but 1 oxygen. This does not follow the law of conservation of mass. The number of the atom has to stay the same. Okay, that is why we need to balance it. And to balance it, if I add 2 in front of hydrogen and 2 in front of water, we will end up with 4 hydrogen on the reactant side, 2 oxygen on the reactant side, also 4 hydrogen on the product side, and 2 oxygen on the product side. And as you could see, the number of the atom is the same. The only thing that changes the arrangement, because on the reactant side we have 2 hydrogen atoms bonded, 2 oxygen atoms are bonded, but in the product side we have hydrogen bonded to oxygen, as you could see here. Okay, whereas on the reactant side we have hydrogen and we have oxygens. Now let's talk about J.J. Thomson. He was an English physicist. He discovered electrons. Okay, he discovered the fact that electrons are the smaller and more fundamental part of the atoms. He also discovered that electrons are negatively charged species. In addition, he proposed that electrons are way more smaller and lighter than the atom. They're the smallest part of the atom. Also, all elements, regardless of whether they are atoms or molecules, they all contain electrons. Okay, then the number of electrons is different in different substances. He also proposed that since atoms are on its own is neutral charge, there should be some positively charged species that balance out the negative charge of the electron. Okay, he only proposed this fact. Okay, when it was his time, they did not know anything about proton. The only thing that he discovered electron, but they said, wait a minute, the atoms on their own, they are neutral charge. Then if electrons are part of the atom and they are negative charge, it has to be some positively charged species to balance out the negative charge of the electron. The next scientist is William Thomson. He was an Irish physicist, and he proposed the plum pudding model. You might have heard of it in the past, or if you have taken chemistry at high school, you might have heard of it. Then what it is that he assumed of a raisin cake, like this picture. Okay, then the sponge of the cake is the sphere of positive charges, and the raisin itself is the electron. Okay, then what he said was that electrons are held in the sphere of positively charged species. Okay, then one more time. Then the sponge, if you think about a raisin cake, the sponge will be the positive charge, and the raisin is going to be the electrons. Okay, then the electrons are held in the sphere of positively charged species. That's what he proposed. But what happened was that the next scientist, Ernest Rutherford, he was a physicist, a British physicist, and what he did was that he explained the nuclear atom using the gold foil experiment. Okay, then by doing this experiment, what he did was that he did a gold foil experiment. Okay, then what it is was that he had a source. Okay, and that source was alpha particles. That source produced alpha particles. Okay, then that's the lead, and that's the source. The source produces alpha particles. Okay, and he put it toward the gold. Okay, a thin sheet of gold foil. Okay, and all around it, as you could see in this picture, are detectors. Then if William Thomson, what he said was correct, what he would have expected that all these alpha particles would go directly through the foil, the gold foil. If what William Thomson suggested was accurate, that's what he was expected to see, then all the alpha particles go through the foil. But this is not what happened. What happened was that not all alpha particles went through the foil. Some of them actually bounced back, as you could see in these pictures. You see some of it are going through, but there are some that are bounced back. Okay? And that's the thing that made him thinking that what the previous scientist, William Thomson, was proposed is not accurate. Electrons are not held in the sphere of positively charged species. Okay? And that's when he discovered protons. Okay? Then what it is that if electrons were held in the sphere of positively charged species, the alpha particles, okay, would go directly through it, but it did not. Okay? Some of them bounced back. That means is that electrons are not held in the sphere of positively charged species. What it is that at the center of the atom are the protons. The protons are at the center of the atom. Okay? And what happens is that when alpha particles hit the center of the atom, some of them bounce back. Okay? That's what happens. Okay. He also suggested that electrons travel around the nucleus, and they travel around the nucleus at a relatively large distance, okay? And protons are at the center of the atom, okay? And they are positively charged species. Then going back to the gold foil experiment, think about it. Then positive charges or negative charges, they repel each other, whereas positive and negative attract. Okay, then what happens is that some of these alpha particles, they hit the center of the atom, where we have the positive charges. That's why those ones that hit the center of the atom, they bounce back. But those that went through the sphere, which is outside the nucleus, they just went through the foil. That's exactly what's happening. Later on, Rutherford, with one of his students, Chadwick, they discovered neutron. What they said was that, okay, at the center of the atom is nucleus. And there are protons, but center of the atom is very dense. Only protons on its own cannot contribute to the weight or to the mass of the atom. Then there has to be another species other than protons that contribute to the mass of the atom. And that's why they discovered neutrons. The next thing that discovered is that neutrons cannot have any charge, because protons take care of the negative charge of the electron. Then you don't want to have any more either positive or negatively charged. Okay, that's why neutron, they discovered that it has no charge. Then Rutherford and Chadwick, they discovered neutrons, and they discovered the fact that neutron has no charge at all. Okay, then just quickly let's go over the plum pudding experiment. Then if William Thomson's suggestion was correct, when we shone alpha particle, it has to go through, okay, if it would have been correct. But what happened was that some of the alpha particles, they hit the center of the atom, okay, and that's why they bounce back. Then what William Thomson was said, which is electrons are held at the sphere of positively charged species, is inaccurate. What it is that at the center of the atom, we have positively charged species, and right outside is where the electrons are. That's what Rutherford proposed after doing the gold foil experiment. And later on, with the help of one of his students, Chadwick, they discovered neutrons. All right, then let's quickly go over the structure of the atom. It's made of electrons, protons, and neutrons. Electrons are outside the nucleus. Protons and neutrons are inside the nucleus. Electrons, they contribute to the size of the atom. An electron contribute to the size of the atom, whereas protons and neutrons, they contribute to the weight, to the mass of the atom. Then as you could see in this table, if you compare the relative size of protons and neutrons in comparison to the electron, you will see electrons almost massless. You see how little it is? That's why we say electrons do not contribute to the mass of the atom. It's only protons and neutrons, okay? Whereas electrons only contribute to the size of the atom. Electrons are negatively charged species. Protons are positively charged species. And neutrons have no charge at all. Now let's quickly go over our conclusion one more time. Then at the center of the atom, we have protons and neutrons. This is the nucleus, which is at the center of the atom. And right outside, okay, that's where the electrons are. Okay. Then inside the nucleus, we have protons and neutrons. And outside the nucleus, we have electrons. Electrons contribute to the size of the atom. Protons and neutrons contribute to the mass of the atom. Protons are positively charged species. Neutrons have no charge. And electrons are negatively charged species. Okay? Then if it's the center of the atom, which contains protons and neutrons, the further the electron gets from the center of the atom, the size of that atom is larger. Then assume, okay, this is where our electron is, and this is where our electron is. Compare the two. You see, the further away the electron is from the nucleus, the larger it's the size of the atom. Okay? And which electrons? And when we talk about electrons, we talk about core electrons, and we talk about outer shell, or they also called valence electrons. Okay. Then valence electrons are those electrons at the outermost layer. Okay, they are at the outermost layer, whereas core electrons are the rest of the electrons. Then when we are talking about the size of the atom, we only look at the valence electrons. Okay, you look at the position of valence electrons from the nucleus. Okay, we don't care about core electrons. Core electrons are stationary, you cannot touch it. But it is those valence electrons that we could touch it. Okay, then the further is the valence electron from the nucleus, is the larger the size. Okay, and different elements on the periodic table, their valence electron is different. That's why the size is different. The elements on the periodic table do not have the same size. All right. Then again, one more time. Then inside the nucleus is where the protons and neutrons are. The nucleus, or protons and neutrons, they contribute to the mass of the atom. Okay, or nucleus is the densest part of the atom. Electrons are outside the nucleus. Okay, and what do we mean by electron cloud? What it is that since the electrons move at a really fast speed, that's why we see them as a cloud. Okay, you cannot just say, oh, I saw that electron in this part. You can't say it. Because they move around the nucleus at a really fast speed, we will see it in the form of electron cloud. Okay, that's what it means. And right outside the nucleus is where the electrons or electron cloud is, and they contribute to the size of the atom, or the volume, which is this size. Okay, and the further is that valence electron from the atom, the larger is the size of the atom. Now let's continue with the structure of the atom. Opposite charges attract each other. Okay, as you can see in this picture, positive, negative, which are opposite charges, they attract. And similar charges repel. Okay, that means positive, positive repel, negative, negative repel. Okay, then if you think about protons and neutrons and electrons, then electrons and protons attract each other. Whereas two electrons next to each other, they repel each other. Okay? That's what holds the structure of the atom together. The nucleus is positive charge, electrons outside are negative, positive, negative repel, positive, negative attract. That holds the structure of the atom together. Okay? It's that attraction between the nucleus and the electron cloud. Now let's talk about atomic numbers. Atomic numbers are the number of protons. Okay? An atomic number is the number of protons. That's what atomic number means. Different elements have different atomic number. You cannot have two elements with the same atomic number. It's impossible. Then if you look at your periodic table, okay, you will see each element has its own atomic number. Atomic number, that's how the periodic table is organized. It's based on the atomic number of the element, which is the number of protons. Okay, right? Then when you have a neutral atom, that means the atom is not charged at all. Okay, its atomic number is equal to the number of electrons. If it's a neutral charge atom, then in a neutral charge atom, the number of protons is equal to the number of electrons. Okay, then if I go back to my previous example, this is the atomic number for lithium, which means lithium has 3 protons. Okay, now since lithium is not charged, by charge I mean like lithium positive, okay, it has a charge on it, or chlorine negative. These are charged atoms, okay, or magnesium 2+. Then these are charged species. When they are not charged, they are neutral. They're just Li, lithium, chlorine, magnesium. These are not charged. Okay. Then for a neutral charge atom, the number of protons and neutrons are the same. Okay. Then for lithium, its atomic number is 3. Since it's neutral charge, its number of electrons is also 3. Also keep in mind that the number of protons, electrons, and neutrons are a whole number. If you look at your periodic table, okay, if it's not a whole number, just round it up and make it a whole number. Okay, the number of protons, that's how the atomic table is set, it's always a whole number. That's for the number of protons, which is the atomic number. It's always the whole number. Some periodic table, most of the periodic table write the atomic number up top, but some of it write it at the bottom. Then for you to know which is which, okay, the one that follows the order of the periodic table, which it goes from left to right, top to bottom, the one that follows the order, that's your atomic number. Okay. Now, mass number, it's the number of protons and the number of neutrons. That is mass number. It's the combination of the number of protons and neutrons. Okay? Then if you look at chlorine, the atom of chlorine, okay, it has its atomic number, which is the same as the number of protons, is 17. Okay? Since it's neutral, its number of electrons is also 17. Okay? And its mass number is 35. Then mass number is the sum of protons and neutrons. And you already know from the atomic number, the number of protons is 17. You could easily find the number of neutrons, which will be 35 minus 17. Which will be 18. Okay. Therefore, the atom of chlorine has 17 protons, 17 electrons, and 18 neutrons. Okay. Let's do one more. Okay. Let's do one for let's do magnesium. Okay. The magnesium is 12 and 24. Okay. Then how would you know which one's which? The one that follows the order of the periodic table is your atomic number. Then as you could see here, 12 is the atomic number. That's why magnesium, its number of protons is 12. Since it's neutral charge, its number of electrons is also 12. And what would be its number of neutrons? That's the mass number, okay, which is 24, which is the total. This is the combination of protons and neutrons. Okay, we know protons is 12, and if you do the math, neutrons going to be 24 minus 12, which is going to be 12. Okay, then magnesium, the atom magnesium has 12 protons, 12 electrons, and 12 neutrons. Okay, now let's talk about a charged species, like this. Okay, oxygen, which is 2 negative. Now it's charged. But what you want to do is that look at the periodic table. Look at the atom oxygen on its own, okay, which is 8 and 16. Okay, on its own. Okay. Then as you could see here, the number of protons never changes. No matter if your species is charged or not charged, the number of protons, the number of neutrons, it always stays the same. It's only the number of electrons that changes. Okay, but for the protons and neutrons, always stays the same because we can never ever touch the center of the atom. Okay, it's only those valence electrons that we could either add or remove electrons. Then what it is that if you remove electron, your atom turns positive. Why? Because electrons are negatively charged species. Then you are removing the negative charge. Your atom turns more positive. And if you add electron, your atom turns negative. Okay? Because you're adding more negative. Okay? Electrons carry negative charge. Then if you remove the electrons, you are removing the negative charge. Your atom becomes positively charged. If you add electrons, which they carry negative charge, your atom becomes more negative. Okay, it becomes a negatively charged. Okay. Now, what we're gonna do, we're gonna write the number of protons, neutrons, and electrons for oxygen. Okay, that's the ionic oxygen. Okay, then when your atom becomes charged atom, we call them ions. Okay, that's what ions mean. It's a charged atom. Now here, the oxygen 2 negative, it's an ion. Now you want to know what's the number of electron, proton, and neutrons. Then look at the periodic table. When you look at the periodic table, that's what you see for oxygen. Okay, then you will see its atomic number which is the number of proton, is 8, you will see the mass number, which is 16, equal to proton plus neutron, which is therefore 16 is equal to 8 plus n. And by doing that, you will know n is 8. Then as you could see, its number of protons and neutrons is the same. Okay, it will not change for ionic species. Always stays the same. The number of proton and neutron, whether you're dealing with an atom of that same species or its ion, is always the same. It's the electron that changes. Then for a neutral oxygen atom, you would have expect the electron to be 8. That's for a neutral oxygen atom. But it's not neutral, it's charged. It's 2 negative. That means you added 2 electrons. Then what it is that instead of 8, it's 10. Okay? Then if one more time, if it would have been neutral, the number of protons and electron would have stayed the same. But it's not neutral. Your oxygen is 2 negative. That means we've added 2 electrons. Then instead of 8, it's 10. Okay? Then oxygen ion has 8 electrons. Sorry, it has 8 protons, 10 electrons, and 8 neutrons. Okay? Now let's talk about isotopes. Isotopes are atoms of the same elements with the same number of protons or same atomic number but different number of neutrons or different mass number. Okay, that's what it is. That's the definition of isotopes. Then isotopes are the atom of the same element with the same number of protons or the same atomic number but different mass number. Okay. Every single element on the periodic table that you see comes in the form of isotopes. Okay. Like for example, if you look at sodium in this particular example, okay, these are the isotopes of sodium. Then as you could see here, in this particular example, as you could see, the mass number is written up top, the atomic number is written at the bottom. Okay, that's some periodic table that's written that way. Then this is the atomic number, and this is the mass number. Okay, then since it's neutral, its proton is, as you could see, is 11. Then the number of electrons also going to be 11. And the mass number is what? Mass number is 23 minus, sorry, it's neutron. Sorry, let me do that. Let me erase that. And its number of neutrons, it's going to be mass number 23 minus the number of proton 11, which will be 12. That's for this sodium isotopes, 2311. Now if you look at the second isotope of sodium, again that 11 is its atomic number. And as you could see, it's the same. Okay, it's 11 protons. And since it's neutral, it will have 11 electrons. And 24 is its mass number. Okay, then its neutrons going to be 24 minus 11, which is 13, as you could see here. And as you could see here, the number of protons are the same, both 11. It's the number of neutrons that changes. Then sodium with mass number 23 has 12 neutrons. Sodium with the mass number 24 has 13 neutrons. That's the definition of isotopes. You don't need to memorize the isotopes of each element. What you need to understand is the definition, and if I give, you have to figure out the number of, how to calculate the number of electron, proton, and neutrons for different isotopes. Okay. Now let's talk about the periodic table of element. Okay. Then the periodic table of the element shows all of the known elements and is set in the order of increasing atomic number. That's how the periodic table is set. It's set based on the increasing the atomic number. Okay. Then this is a typical periodic table, okay, which I got it from your textbook. Then what I mean periodic table is based on the increasing atomic number. Okay, then look at it. Then if you look here in this particular picture of the periodic table, then you will see it goes on the left hand side, which the hydrogen is, the atomic number is 1. On the right hand side, helium is 2. Then go back to lithium, 3, beryllium, 4, boron, 5, carbon, 6, nitrogen, 7, oxygen, 8, fluorine, 9, neon, 10, okay, sodium, 11, magnesium, 12, aluminum, 13. That's what I mean. The periodic table is set based on the atomic number, okay? It's in the order of the increasing atomic number. And the periodic table always go from left to right, top to bottom, okay? On the left hand side of the periodic table, that's where the metals are. The metals on the left side. Non-metals on the right side. Okay. And here between group 2 and group 3, we have a group that's called transition metals. Okay. Transition metals are metals, first of all. But what it is that they have different charges. Okay. Then basically, when we talk about the periodic table element, group 1, okay, group 1, or do these A's, let me go over it another way. You will see those A's, 1A, 2A, 3, 4, 5, 6, 7, 8 A's. These are the major group elements. By major group element, they have only one specific charge. Okay. Whereas transition metals, they have 2 or more charges. Okay. That's the difference. There is exception. Okay. The exception is silver and zinc. That's the exception to the rule. Silver and zinc, only one charge. But the rest of the elements that are in transition metals, they have 2 or more charges. Whereas the major group elements, like 1A, 2A, 3A, 4, 5, 6, 7, 8A, They only have one set charge. Down here are lanthanides and actinides. What they are here, they are part of the transition metal. Okay, they go here and here. Then if you would have put this, it would have messed up the periodic table. That's why they are positioned underneath of the periodic table. And they call lanthanides and actinides. Okay. Group 1, this is group 1, okay? Group 1, okay? 1A is group 1, 2A is group 2. And these are our metals, okay? Group 1 metals are called alkaline metals. Group 2 metals are called alkaline earth metals, okay? That's the difference between group 1 and group 2. Now let's talk about hydrogen. Hydrogen is a nonmetal. And it's the only nonmetal that plays on the left side of the periodic table. Remember, left side of the periodic table is where all the metals are, with the exception of hydrogen. Hydrogen is the only nonmetal that's placed on the metal side. If you look at some of the periodic table, sometimes they put it here, right here next to helium, because since helium is a nonmetal. Okay. But some periodic table put it there, some periodic table put it right here, right above lithium. Then lithium, then this group, starting from lithium to francium, these are all metals. All group 2 metal, okay. Group 7, starting with fluorine, chlorine, bromine, iodine, these are halogens. Last group is group 8, which we call them noble gases or inert gases. These are, they do not participate in any chemical reactions because they have reached their most stability. You will not see any reaction involving group 8, okay? Unless we force them to do so. That's the characteristics of group 8. That's why we call them inert gases or noble gases. They don't do anything. Then all the other elements on the periodic table are either going to lose or gain electron just to look like group 8 nonmetals. Okay? Why they are inert gases? Because they have reached their lowest energy level. Lowest energy level is where all the atoms are the happiest. Okay, they're relaxed. Then all the other elements, they're going to gain or lose electron to reach that lowest energy level. That's where the happiest they are. Okay. Then group 1, starting with lithium. Group 2, some of the elements in group 3 are metals. Group 4 with carbon. Group 5 with nitrogen. Group 6 with oxygen. Group 7 starting with fluorine. And group 8 starting with helium. These are all nonmetals. Between major group 2 and 3, we have transition metals, and then we have lanthanide and octanides. Then transition metals, lanthanide and actinides, these are all metals, but they have 2 or more charges. Whereas major group elements, what they have one specific charge assigned to them. Okay? Now let's talk about metals. As I told you guys in the previous slide, metals are on the left side of the periodic table. Metals are good conductors of heat and electricity, and they are soft. You could pull them into wires or hammer them into tin foils or sheets. They are very shiny, and they are extremely reactive with the oxygen in the air. That's why when you want to look at whether a metal is shiny or not, like when you're making observation, you have to use the sandpaper to get rid of the oxidized layer. Okay, then you will see how shiny it is. And also metals want to lose electrons. Okay, when they go under chemical change, metals lose electrons. That's a very important. That means they become positively charged species. okay, like lithium ion, calcium ion, and etc. These are metals. Then they lose electrons. They become positively charged species. Non-metals, as we discussed, they are on the right side of the periodic table, with the exception of hydrogen. That's the only one that's right above lithium. They are poor conductors of heat and electricity. They are very hard and dull. Look at carbon or diamond. You see how hard it is? They have so many different properties. Metals are all solid, but non-metals, some of them are solid, some of them are gases. Okay, like carbon is solid at room temperature. Okay, whereas oxygen, which is a non-metal, just like carbon, it's gases. Okay, as you could see, they have different properties. Non-metals gain electrons. Okay, they become negative charged species. Okay, when they become in ionic form, they gain electron. Okay, like oxygen to negative. Nitrogen 3 negative. Okay, chlorine 1 negative. You see, they gain electron. That's why when they become ionized, they become negatively charged ion. Next ones are metalloids. Metalloids, they go along the zigzag line. Then if I go back to my periodic table, do you see this zigzag line? Okay, that's where the metalloids are. On periodic table that you're provided with, the zigzag line is not on it, because you have to know which ones are metalloids. Okay, but they lie around the zigzag line. Then as you could see here, what it is that some of them are, okay, they are metalloids or semi-metal, which means sometimes they have the characteristics of metal, sometimes they have the characteristics of non-metal. Okay, and that's why we call them metalloid or semi-metal. Okay, then these are semi-metals or metalloids. Just memorize that. Okay, like boron, silicon, germanium, etc. These are the metalloids, and we have only these. Okay, the rest are either metal or non-metal, and this needs to be memorized. Okay, just they go along the zigzag line, that's all it is. Okay, sometimes they have characteristics of the metal, some of them have the characteristics of non-metal. Okay, then we're gonna do this example. Let's do this example. Then on this example, you want to look at your periodic table and give the atomic number, the group number, and say whether it's a metal, non-metal, or metalloid. Look at zinc. Okay, zinc, its atomic number, I call it A number. It's 30. Okay, then if you look at the periodic table, it is on the transition metal. That's where the zinc is. Okay, it's a transition metal. Okay, and what group does it belong to? Then let's go and look at the periodic table. That's where zinc is. You see it? Right here. Okay, that's in group 12. That's where it is. It's in group 12. Okay, then we gave the atomic number, group number, and say whether the element is a metal or non-metal or metalloid. Okay, next one. Sodium. Look at the periodic table. I missed the periodic. Sodium. It's right here. It's in group 1. It's a metal. The group is alkali metals. Okay? That's where the sodium is. And as you could see, its atomic number is 11. Okay? Then its atomic number is 11. It's in group 1. Okay? Which we call them alkali metal. And it's a metal. Barium. Now let's do barium. Okay? Barium, Ba. Then if you look, is in group 2. Okay? Okay? Which is part of alkali earth metal. And it's on the left hand side of the periodic table, then it's a metal. Okay? And its atomic number, forgot to say, is 56. Now let's talk about silicon. Si. Okay? Its atomic number is 14. It's in group 4, the major group 4 on the periodic table. That subgroup starts with carbon. And it's a semi-metal. Okay? It's lying along the zigzag line. Or a metalloid. Iodine. Its atomic number is 53. It's a halogen. Okay? Then it's in group 7. It's a halogen, and they are nonmetals. Krypton, Kr. Its atomic number is 36. It's in major group 8. It's an inert gas or noble gas, whichever you want to write down. And also a nonmetal. Okay? And that's how we do this problem. Basically, you don't need to memorize the position of any of these elements. Just when you're doing this specific problem, have a copy of the periodic table right in front of you and just look it up. The whole purpose of this example is for you guys to get familiar with the position of each element. Rather than taking a long time for you to find it, when you practice it, you kind of have an idea where you should be looking for. But you don't need to memorize. You don't need to memorize the atomic number. You don't need to memorize which group that belong to. Okay, you could always refer to the periodic table, and you will always be provided with a copy of the periodic table. Okay. Now let's talk about the state of elements in nature. One is diatomic molecules. Diatomic molecules are those molecules made of only 2 identical atoms, like oxygen, nitrogen. Then these are some of the exceptions. Like when we talk about lithium, it's a lithium atom. That's what you write. We talk about like carbon atom. That's what you write. But you have to keep in mind, there are some atoms, even though we call it an atom, but it's written in diatomic form, like oxygen atom, nitrogen atom. Then we don't have, when we say there is a reaction with oxygen atom, you don't write oxygen on its own. You write O2. Or when we are talking about nitrogen, you write N2, because they come in diatomic form. They don't come singlet. Okay, then these are the diatomic molecules. Okay, these are all the halogens from group 7. Including hydrogen, nitrogen, oxygen. Then when later on we write chemical equations, starting chapter 7, when I talk about that there is a reaction with oxygen atom, you don't put O. You have to immediately remember that, oh, that's a diatomic. Then you have to write it as O2 instead of O. Then memorize these. These are the molecules that they come in diatomic form, okay? Just note all these 3, 4, 5, 6, 7. These 7 only. You don't need to memorize the state, the elemental state, whether it's a gas or a liquid. You don't need to know any of it. The only thing that I want you to know is that these 3, 4, 5, 7, these 7, they come in diatomic form. That's all I want you to memorize and know it. Okay. The second one, then the first one was diatomic. The second one is allotropes. Allotropes are different form of an element. For example, carbon comes in graphite form, it comes in diamond form. That's graphite. This one is diamond. Okay. And as you could see in the next slide, it's all carbon. Each of these black spheres is a carbon. You see, it's just the bonding between carbon atoms. That's all it is. It's just carbon. Okay? But depends on how they are bonded together. One would be graphite, one would be diamond. And as you could see here, diamonds are a lot harder to break because of the way all these carbon atoms are bonded to each other. Whereas graphite, in comparison to diamond, it's easier to break. In some industries, they use diamonds as cutting tools. Okay, now let's talk about ions. Okay, then what's the definition of an ion? When an atom either gain or lose electrons, it forms ion. Okay, then ionic compounds, they are oppositely charged ion, and the bond that holds those ions together is an ionic bond. Okay, and we have two types of ions, cations and the anions. Okay, then ions or ionic compounds, what it is, it's made of an ionic compound. It's made of a metal and a non-metal. Okay, the metal, as we discussed, it always loses the electron. Okay, becomes cation. Non-metal gains electron, it becomes anions. Okay, and the bond that connects the two is an ionic bond. Let's go back to our sodium chloride. And that bond is an ionic bond. Then what happens is that sodium is a metal, is in group 1. It loses the electron. Chlorine is a non-metal, is in group 7, halogen. It gains the electron. Then sodium loses its electron to chlorine. That's why they are bonded. And the bond is ionic bond. Now let's talk about cations. They are positively charged species. Metals are cations. Okay? Metals are cations. Either could be major group metals or transition metals, which include lanthanide and actinide. These are all metals. They all lose electrons. Okay? And since metals lose electrons, their number of electrons is less than proton because they are losing it. Okay? Now look here. For this specific example, it's magnesium and magnesium ion. Okay? Then magnesium is magnesium here. Let me write it down here. The atom magnesium, if you look at the periodic table, is 1224. Right? Now, but just by looking at it, just write it down. Look at the atomic number, it's 12. Then it has 12 protons. Since it's a neutral charge, its number of electrons is also 12. And its neutron is 24, which is the mass number, minus atomic number, which is 12. Okay? Then right inside the nucleus, here is the nucleus. The protons is 12 and the neutrons are 12. And right outside the nucleus, that's where the electron cloud is. Okay? And it has, as you could see, 12 electrons. Now let's do the same thing for ionic magnesium, or magnesium cation. Then the number of protons and neutrons is the same as the neutral charge element. Okay? Then as we did in the previous one, the magnesium atom on its own, it has 12 protons and it has 12 neutrons. It's the number of electrons that's the only one that changes. The magnesium is 2+. That means it has lost 2 electrons. Then if you think about the neutral element magnesium, as you could see here, it had the electron, it's 12. It has 12 electrons. But the ionic or the cation magnesium is 2+. That means it's losing 2 electrons, which means 12 minus 10. Sorry, which is 12 minus 2, which is 10. Okay? That's what happens. All right? The neutral charge magnesium has 12 electrons. It has the same number of electrons as the number of protons. But once it becomes charged, okay, the magnesium ion is losing 2 electrons. That's why it's 2 positive. Then it's 12 minus 2, which becomes 10. Now let's compare the relative sizes. Then, as we discussed in one of the first slides, it is the electron that is in charge of the size of the atom. Then look here. This one is magnesium atom that has 12 electrons. That's the magnesium ion that has 10 electrons. Okay. Then the less electron that you have, the smaller the size is. That's why the size of the magnesium atom is larger than the size of the magnesium ion. Okay. Then the relative size, that's a better way of saying it. Relative size of magnesium atom is larger than magnesium ion. Okay, because magnesium atom has more electron than magnesium ion. Magnesium ion has 10, magnesium atom has 12. Okay. Now, let's talk about anions. They are negatively charged ions. They have more electron than protons. Because they are negatively charged, they gain the electron. Okay. And nonmetals, they gain the electrons. They gain 1 or more electrons to form ions. Okay. All right. Then that's an example for anions. That's the definition of anions. They are negatively charged. They have more electrons than the protons. And they gain electrons. Okay. Now let's look at this example. Okay. Let's look at comparing chlorine and chlorine ion. Then chlorine, if you look at your periodic table, is 17 and it's 17. Okay. 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 Then chlorine. Okay. It's 17 and 36. It's 35.5, just round it up to a whole number. Okay, then when you do that, based on what it is, its number of proton is 17, electron is 17, and neutron is 36 minus 17, which is 19. Okay, now let's look at chloride ion. Okay, for chloride ion, as you could see, chlorine, the neutral charge chlorine, is gaining 1 electron and it becomes chlorine minus, or chloride ion. Then, as we discussed before, the number of protons and neutron always stays the same, never ever changes. It's the electron. Then from chlorine atom going to chloride atom, it has 1 extra electron. The number of electrons for chlorine atom is 17. Then for chloride ion, since it has 1 extra electron, is 17 plus 1, which is 18. Okay, that's what it is. Then inside the nucleus, that's where the protons and neutrons are. You have your proton, which is 17, neutron, which is 19. Okay, and right outside, that's where the electron clouds are. And that's where you have 17 electrons. This is for neutral chlorine atom. Okay, now for chloride ion, again, this is the nucleus. And that's where the protons and the neutrons are. Remember, we can never ever touch the number of protons and neutrons. We can't touch the nucleus. And right outside is where the electrons are. You see it in the form of electron cloud. And that's, you see the number is 18. Then if you compare the chlorine atom and chloride ion, as you could see, chloride ion has 1 more electron. Then let's talk about the sizes. Then it is the number of electrons that indicate the size. The higher number of electrons, the larger the size. Then as you could see, the relative size of the chlorine atom is smaller in comparison to chloride ion. Then let's write it down. Relative size of chlorine atom is smaller than chloride ion because chloride ion has more electrons than chlorine atom. Then chloride ion has 17 electrons, whereas chlorine atom has only 17. That's why the relative size of the chlorine atom is smaller, as you could see in this picture. Okay. Now, the next thing that I want you guys to memorize for the time being is the ionic charges for the metal and the non-metal. For transition metals and lanthanide and actinide, since they have 2 or more charges, we will give it to you guys. You don't need to memorize it at all. But for major group element, you have to know. Then memorize that. Group 1 metal, they're all positive 1. Group 2 metals, they're all positive 2. Group 3, those metals are positive 3. Okay, group 4 consists of carbon. It consists of carbon, silicon, germanium, these ones, with the exception of these 2, they have more than these 2. Okay, have more than 1 charge. These are the exception to the rule. But the rest, group 4, they don't form ions. They don't gain or lose electrons. Okay, they only share electrons. That's why they won't become charged. Group 5, okay, nitrogen, phosphorus, arsenic, these are all become negative 3. Okay. Group 6, as you could see, They are all -2. Group 7 is -1. Group 8, they are inert gases. They don't participate in chemical reaction. That's why it's just nothing. Then I want you guys to memorize. Group 1 metals are all +1. Group 2 metals are +2. For group 3, these 3 only are +3. Okay, then these are metals. For non-metals, group 7 is -1. Group 6 is -2. And group 5 is -3. I want you to memorize it, okay? It's going to be -3. Okay, that's what I want you to do. That's your homework for today. Or for while you're listening to this part. Memorize the charges. And hydrogen, which is here, okay? Hydrogen depends on what's reacting with. Hydrogen has either a positive or a negative charge. If hydrogen reacts with metal, then its charge is -1. If it reacts with non-metal, its charge is +1. That's for hydrogen. Then it looks what is reacting with. Okay. Now let's talk about chemical compounds. Okay. When we are talking about chemical compounds, you could represent it in terms of chemical formula or structure of formula. Then chemical formula, like carbon dioxide, like CO2. Okay, this is carbon dioxide. Okay, CO2. Then the information that you get from it is that this compound consists of carbon and oxygen, and it has 1 carbon and 2 oxygen. That's all the information that you get from chemical formula. Structure formula, it gives you all the information that you need. Okay? It tells you that this compound consists of carbon and oxygen. It tells you it has 1 carbon, 2 oxygen, but it gives you a lot more information. It tells you all about the bonding, how these atoms are bonded to each other. It tells you whether it's a single bond or double bond. It talks about non-bonding electrons. Okay? Then it shows you everything that you need to know about that compound. Then chemical formula does not give you enough information, whereas a structural formula gives all the information that you need regarding that specific compound. Then that's the difference between chemical and structural formula. Now let's talk about ionic compounds. Ionic compounds, the name defines it. It's made of ions. Then ions make ionic compounds. What are the characteristics of ionic compounds? They have high melting point. They are good conductor of heat and electricity only if they are melted or dissolved in water. Okay? If it's not in either these two conditions, they do not conduct electricity and heat. Okay? Then they become a good conductor of heat and electricity if they are melted or if they are dissolved in water. When a compound dissolves in water, the state becomes aqueous, which is aqueous, and it comes from aqua, which in Greek means water. Then when we dissolve a compound in water, do not write the state as liquid. It's not liquid. It's aqueous, okay, which we write it as in AQ. ionic compounds, they are neutrally charged. Okay? What that means is that the sum of charges of the cations and the anions must be 0. Then ionic compounds are made of ions. It cannot make up two anions or two cations. It always is made of a cation and an anion. That's what makes an ionic compound. Okay? The cation loses the electron, give it to the anion. And as you could see, they are neutral charged species. Okay? What does that mean? Look at this example. Okay? Magnesium chloride, MgCl2. Let's look at the periodic table. Let me go back to my periodic table. Then ionic compounds is made of metals and a non-metal. Okay? Let me go back. Okay. I jumped it. Okay. The magnesium is here, it's a metal. Chlorine is here, is a non-metal. Okay? That's an ionic compound. We can never ever have a reaction between two metals. Impossible, never happens. Okay? But we could have a reaction between two non-metals. When we have a reaction between two non-metals, that reaction or that compound, it's not an ionic compound. We call it a molecular compound, which I'll talk about in more depth on the next chapter. Okay? But let's go back and talking about ionic compound for now. Then as you saw on the periodic table, magnesium is a group 2 metal. Chlorine is in group 7 and it's a non-metal. Then once you know you have a metal and a non-metal, that compound is for sure an ionic compound. Okay. Now, what does that mean that the sum of the charge is 0? Let's go back to our periodic table. Okay, let's go back. Go back. We can do it right here. Okay, magnesium is right here. It's in group 2 and it's a metal. Then you should know it's a metal, then its charge becomes positive, and it's in group 2, it becomes positive too. Now look at chlorine. Chlorine is right here. Then what would it be? It's in group 7 and it's a non-metal. That's why it's -1. Okay, remember I told you guys to memorize the charges. Okay, and let's go back to our example. So I went the other way, sorry about that. Let's go back. Okay, then the way that we write it, since you know magnesium is +2 and chlorine is -1, then what happens is that the cation gives its charge, which is +2, okay, goes as a subscript on the chlorine without the charge, and the charge on the chlorine goes as a subscript on the magnesium itself without the charge. Then what happens is that it becomes MgCl2, and we don't write 1. Okay, it should have been like that, but we don't write the 1. That's why I'm going to just take it off. Now you want to see if the sum of the charges is 0. Okay, we're going to solve for it. Look at this. Magnesium, as you could see, look at the formula, MgCl2. Okay, magnesium, then the way that we write it for magnesium chloride, this compound, as you could see, consists of 1 magnesium and 2 chlorine, and we want the sum of all charges to be 0, right? Then what is the charge of magnesium? Magnesium is in group 2, it's a metal, it's +2. Chlorine is in group 7. It's a non-metal, is -1. Then look here. 2 minus 2 is 0. That's what we mean by, if you wrote the formula for ionic compound correctly, the sum of the charges has to be 0. And that's what I mean by it. Then when we are writing a formula for ionic compound, the charge on the metal goes as a subscript on the non-metal, and the charge on the non-metal goes as a subscript on the metal. Don't write it as superscript. Don't write it like this. Okay, this is wrong. Don't write it like that. Okay, that's wrong. The charge is switched. Okay, also you don't have to put any charges. Okay, compounds are neutral charge. They do not have any charges at all. Okay. Okay. Now let's do this problem. You're gonna write down the formula. Okay, for K and I. I have given you the charges, but if I would not have given you the charges, look at potassium. Potassium is in group 1. Okay, it's in group 1, it's +1. Okay, right here. Iodine is in group 7, is -1. Okay, then what happens is that's why potassium is +1, iodine is -1. You don't need to write the 1, that's why we just leave it as plus and negative. Then what happens is that potassium, we put it next to each other, and the way that we always put it, the metal always goes first, non-metal always goes second. That's how you have to write it. Metal first, non-metal second. Okay, that's always have to be the case when we are writing ionic compounds. Now that I wrote the potassium first, iodine second, then the charge on the metal without the sign, okay, goes on the non-metal, and the charge on the non-metal without the sign goes on the metal. And we do not write 1. That's why I leave it as this, Ki. This is the molecular formula for an ionic compound consists of potassium and ion. And you could check for yourself if the sum of the charge is 0. This compound consists of 1 potassium and 1 iodine. And we have to know what definition the sum of the charges has to be 0. Then what is the charge for potassium? It's in group 1, it's +1. What is the charge on iodine? It's in group 7, it's -1. And if you look here, +1 minus 1 is equal to 0. That's what I mean by the fact that the sum of the charge is 0 for an ionic compound. Okay, then if you write an ionic compound like something like this is wrong. Okay, it has to be neutral charged. And to double check your work, just solve this for yourself if you want. Okay, to make sure you did it correctly. Now let's do it for magnesium and nitrogen. The magnesium is in group 2. Okay, the magnesium is in group 2. That's why it's 2+. Nitrogen is in group 5. But I told you guys from memorization, for now, know that it's -3. Then we're going to put it together. The metal always goes first, non-metal goes second. The charge on the metal, which is +2, goes as a subscript on the non-metal without the sign. And the charge on the non-metal, which is 3, goes as a subscript on the metal without the sign. Okay, this is the chemical formula for the ionic compound consists of magnesium and nitrogen. And again, you could check it to make sure that the sum of the charges is 0. This compound consists of 3 magnesium and 2 nitrogen. Do you see it? It's 3 magnesium, 2 nitrogen. And the sum of the charges is 0. What is the charge on magnesium? +2. What is the charge on nitrogen? -3. Are the sum of charges 0? Yeah, because +6 minus 6, and it is 0. Then you've done a good job. What you wrote up here is correct. Now let's do strontium and oxygen. Again, we're gonna write metal first, or the cation first, non-metal second. The charge on the cation goes as a subscript on the anion, and the charge on the anion goes as a subscript on the cation without the charge. And then you're gonna balance it out. Okay, you have to simplify it, not balancing it, simplify it. Okay, then you're gonna divide everything by 2, right? It becomes SrO. This is the chemical formula for this ionic compound. Okay, and you could double check it to make sure the sum of the charge is 0. Then this compound consists of 1 strontium plus 1 oxygen, and the sum of the charge is 0. You know the charge on the strontium is +2. The charge on oxygen is -2. And as you could see, +2 -2 is 0. That means the size of the charges are, the sum of the charges is 0. And you've done a good job. Okay? If you don't simplify it, it's wrong. Then the rule says you have to simplify it as much as you could. We cannot have decimals. You cannot have 2.5 strontium or a quarter of a oxygen. It has to be a whole number. 1, 2, 3, 4, 5, etc. Okay? Ionic compound should not be charged at all. Then when you have everything, you could check for yourself if you've done it correctly by doing this little math, but you don't have to. Now let's do manganese and sulfur. Okay? Then as you can see, manganese is a transition metal. Look here. Sorry. Manganese is a transition metal. It's right here. Okay? That's why it's a metal. Sulfur is a non-metal. It's right here. Manganese is a transition metal. You don't know the charge. It has so many charges. That's why you're told it's +4. Okay? There's no other way of knowing it. But sulfur, it's in group 6. All the non-metal in group 6 are not -2. And that's why it's -2. Okay? Now when you put it together, the cation goes first, the anion goes second. The charge on the cation goes as a subscript on the anion, and the charge on the anion goes as a subscript on the cation. Okay? Without the charge. Now, can you simplify this? Yeah, you could simplify everything by 2. Then what do you get? Okay, that's what it is. Okay, then you could want to double check it. Sure, this compound consists of 1 manganese, 2 sulfur, and the sum of the charges for ionic compound is 0. What's the charge on manganese? You're told it's +4. What's the charge on sulfur? Is in group 6, is a non-metal, is -2. And then look, it's 4 minus 4 is 0. Then you've done a good job. Okay? Then basically, when you want to write an ionic compound, the cation or the metal goes first, the anion or the non-metal goes second. The charge on the cation goes as a subscript on the anion without the sign, and the charge on the anion goes as a subscript on the cation without the sign. If when you put it together, if you need to simplify it, we simplify it as much as you can. But you have to make sure the subscripts are whole number. They are not partials. It has to be a whole number. Also, if it's one of the subscripts for one of the species is 1, we don't write 1. If you do write 1, we will dock points because you should not show number 1. This is a copy of the periodic table that you will provide with on all the exams and the quizzes. I've already posted on Canvas, on the lecture shell on campus, the very first topic, that's welcome to chemistry. It's right there, okay? Then one more time, okay? Group 1 is a metal, the charge is +1. Group 2 is all +2. Group 3, some of these, like boron, aluminum, germanium, are +3. Sorry, +3. Now, for We fix it. Now for group 4, starting carbon, they do not form ionic compound, okay, with the exception of these two. Those ones, they form molecular compound, okay, which we talk about on chapter 5. Then they are not charged, okay, with the exception of these two elements. Group 7, starting nitrogen, they're nonmetal, -3. And group 6, starting major group 6, okay, starting with oxygen, they are -2. And group 7, they're all -1. And last group, they are 0 because they are inert gases. They do not participate in any chemical reaction. Hydrogen is a nonmetal. It's usually -1. Okay, but then once it reacts with another nonmetal, as we explained before, sometimes +1, sometimes -1. Okay, then if it reacts with a nonmetal, it's -1. If it reacts with a metal, it's -1. I don't know if I said it right now, but if you react with a non-metal, its charge is positive, and if it reacts with a metal, its charge is negative. Okay, this is the end of chapter 4. Thank you for listening to my lecture.